So we're going to talk about calorimetry, but that requires an initial discussion of heat capacity and specific heat, and we're going to do some practice problems at the end. So let's say we have a gram of water and it's in its liquid phase and it's at a temperature of 14.5 degrees Celsius. If we in 4.184 joules of heat, we can raise the temperature of that water by 1 degree Celsius. So this is sort of an explanation of specific heat. Specific heat is the heat, or Q, lowercase q, required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And so this is just a value that you would see in a table somewhere, like here. And so you see this table with a column for specific heat, and you can see that different substances have different specific heats, which should make sense. You can also see that liquid water has a higher specific heat than solid water, and so that should tell you that a gram of liquid water requires more heat, or lowercase q, to raise the temperature by the same amount as it would to raise the temperature of solid water. And we're going to do some practice problems later to make sure everybody understands this. Now, heat capacity is a much more general term. And usually it refers to a molar heat capacity, which is also listed here. Molar heat capacity is the heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius. And so you can see the units are provided, so it's relatively easy to see which one you're working with. And we're going to do some practice problems with this a little bit later. Now, calorimetry, the idea here is that this is an experimental kind of method where we measure the heat that is released or absorbed by a reaction, and we know what that is because we measure the heat that is gained or lost by the surroundings. And so there's a temperature change in the surroundings. We use that temperature change to identify how much heat was gained or lost by the surroundings, and then we know how much the system gained or lost, right? Because remember, the system transfers its heat to the surroundings and vice versa. And so we can make some conclusions from the heat of the system based on the heat of the surroundings. And so you see the little boxes down at the bottom with the system and the surroundings. And when heat goes into the system, that's endothermic. That means the surroundings will get cold. That means the temperature change will be negative. It'll go down. As opposed to an exothermic reaction, the temperature of the surroundings will go up, and we will see a positive temperature change in that surroundings. And then we know that the system must have lost heat because the surroundings gained heat. Okay, so we'll do some practice problems for this later too. You see a picture at the bottom, sort of on the right-hand side, of what we call a calorimeter. In a calorimeter, you have a thermometer that's going to measure the temperature change, and there's going to be a reaction mixture inside. And of course, you need some good stirring mechanism, and you need some sort of insulated vessel so that there isn't a lot of temperature change based on heat gained or lost from the outside air. Now, in our lab, what we're going to use is just a coffee cup, which is actually shockingly good at measuring temperature changes and insulating away from the external environment. And it's the same idea. You're going to have a stirrer, and you're going to have a reaction that goes on inside, and you're going to measure the temperature change based on the thermometer. Now, there are different kinds of calorimetry. What we're going to be doing in our lab is called constant pressure calorimetry, and that uses the calorimeter like the coffee cup calorimeter. The constant pressure is the pressure of the atmosphere outside. And there's also what's called constant volume calorimetry, and they measure different things. And so constant pressure calorimetry measures delta H, which is the change in enthalpy of the reaction, which is what we're going to measure in our lab. Constant volume calorimetry is a little bit different. It uses what's called a bomb calorimeter, and it has a set volume that doesn't expand at all. And this actually just has a different, there's just a different measurement made. Okay, so this will help you determine the change in internal energy of the system rather than the change in enthalpy. We are not going to be doing any kind of bomb calorimetry this semester or this entire year. But if you continue as a chemistry major and you take physical chemistry, then you will probably do constant volume calorimetry in second semester of PChem. Now we're going to do a couple of practice problems here just to make sure everybody knows how to do these. So here we have a couple of questions. The first one is a calorimetry problem, and the second one is just a relatively simple specific heat capacity problem. We're going to start with the first one. So we have a coffee cup calorimeter, and we're dissolving ammonium nitrate in 75 grams of water. We can see the initial temperature is 25 degrees, and then we can see that the final temperature is 23.34 degrees. So initially we can tell right off the bat that the temperature decreases, which means that this must be an endothermic reaction. So ultimately we're calculating the change in enthalpy delta H, but I can already tell from the information given in the problem that the answer when I'm done should be a positive value, right? So we know that from the beginning. When the temperature goes down, should be endothermic, delta H will be positive. Now let's actually do the problem. So whenever you're calculating the heat associated with some change in temperature, heat, or Q, equals mc delta T. M is the mass of whatever is changing temperature. C is the specific heat of whatever is changing temperature, and delta T is the change in temperature. That would be the T final minus T initial. So the mass of what's changing temperature is the overall mass of the solution. So you have 1.60 grams of solute combined with 75.0 grams of solvent. Altogether, that gives you 76.6 grams overall of solution. That is what's changing temperature. So that is the mass. The specific heat you assume, it tells you here, assume that the solution has the same heat capacity as pure water, which is given here. If it weren't given, it would be at the top of your quiz or homework or test or whatever, somewhere at the front of the exam. But here it's given in the problem, 4.18 joules per gram degree Celsius. So I'm going to write that in my problem here in green, and I underlined it in green up here, and I wrote it in green over here. Finally, the change in temperature is T final minus T initial. So the final temperature is 23.34. We're going to subtract from that the initial temperature, which is 25.00. That's going to give me negative 1.66 degrees Celsius. So it's a negative temperature change. It goes down. You plug all those things in, and this means we're going to get a negative Q, and that's because this is the heat of the surroundings. The surroundings loses heat. That's why it's going to end up being negative, because it loses heat, and it loses it to the system. So remember, in a calorimetry problem, we use the heat that the surroundings either gains or loses, and we then can figure out how much heat the system lost or gained as a result of that. Because remember, the heat that the surroundings loses is the same as the heat that the system takes. So that's how we do these calorimetry problems. That's sort of the whole basis of calorimetry. So here, all of these units are going to cancel out, and we end up getting Q in joules is negative 531.5 joules. Now the heat of the system is equal in magnitude but opposite in sign, and so that's going to be positive 531.512 joules. And up here it asks for delta H, which is Q, but it's in kilojoules per mole. So we need to divide by moles of ammonium nitrate. And the reason we divide by moles of ammonium nitrate is because that's what we're dissolving, right? So that's sort of the analyte in this case. That's what we're analyzing. The heat of solution means what is the heat associated with dissolving a certain compound. So it's that compound that we're dissolving, which means that's what we need moles of. Okay, it would be a different value. We would get a completely different result if we were dissolving a different salt in water. Remember, in lab, you dissolve some salts that got hot and some got cold. So it's the ammonium nitrate that it's per mole of. So now this Q goes up here. We divide by 1,000 to get kilojoules, 0.531512 kilojoules. We need to convert 1.60 grams into moles. We get 0.019987 moles. That goes in the denominator. So delta H is shown here. We get 26.592878. If we figure out significant figures here, the change in temperature is going to give us three significant figures, because 23.34 minus 25.00, we lose that tens place, right? We end up with 3 sig figs. And then our mass will be accurate also only to 3 sig figs. The 76.60 is only accurate to the tenths place. And our heat capacity is only accurate to 3 sig figs. So it looks like everything has 3 sig figs. So 26.6 kilojoules per mole is my answer. It's a positive number like we said it should be. Number 2, specific heat capacity of silver is 0.24 joules per gram degree Celsius. Calculate the heat, that's Q, required to raise the temperature of 150 grams of silver from 273 to 298 Kelvin. So here we're going to use the same equation, Q equals mc delta T. The mass is given in the problem, 150 grams. C is the specific heat, also given in the problem, 0.24 joules per gram degree Celsius. Delta T is the change in temperature. Now that's T final minus T initial. I'm going to plug in the Kelvin temperatures here, 298 Kelvin minus 273 Kelvin, and you end up getting 25 Kelvin. Now what I want to make sure everybody understands is that the units here, so I plugged everything in here, the temperature is going up, right? So there's a positive Q required, and it even specifies what's the heat required to raise the temperature. So it's going to be a positive number, and the reason for that is because you need some quantity of heat, a positive quantity of heat required to increase the temperature or something, right? And so if it said what's the heat associated with raising the temperature, it would be positive because you know heat has to go in to the system, to the silver, right? You also know it's going to be positive because this actually stipulates how much heat is required. So it knows heat's going into the silver, into the system. So here, when you cancel out the units, the grams are going to cancel, and you're going to end up with joules on the top. Now you have Kelvin temperature and degrees Celsius temperature, and so this might be kind of confusing to some people because Kelvin and Celsius are not the same thing. However, because this is a change in temperature, then they are interchangeable. They are compatible units because it is a delta T, not just an absolute temperature T. So in other words, if you converted 273 Kelvin into degrees Celsius, you would get 0 degrees Celsius. If you converted 298 Kelvin into degrees Celsius, you would get 25 degrees Celsius. And then if you used that 0 and 25 to calculate delta T, you would still get 25 degrees Celsius. So I'm not trying to say that 298 Kelvin, that number, 298, is the same thing as 25, because it's not. But the difference in temperature here between the two Kelvin temperatures and between the two Celsius temperatures are the same. Okay, and that's just because converting between Celsius and Kelvin just involves adding a number to it. So you're going to add that number to both values, and because you add it to both values and then you subtract the two values, then you end up getting the same overall difference in temperature. So these are compatible in these problems because it is a difference in temperature that you're measuring here. And if you don't believe me, you could convert them to Celsius every time. That would be fine. You'll still get the same number. It's just more work. So now when you multiply these together, we end up with 900 joules. 150.0 has 4 significant figures. 0.24 has 2 significant figures. And our temperature has 2 significant figures because we're subtracting these two numbers from each other. 273 and 298 are both accurate to the ones place, which means when you subtract the two, they are both accurate. The difference is accurate to the ones place, which has 2 sig figs, 25 Kelvin. So now our final answer needs to have 2 significant figures, and the issue there is that one of those is a 0. So we need to make one 0 significant and the other one not significant. There are 2 ways you can do that. Actually, 3 ways you could do that. When I was in school, we learned that if you put a line above the least significant 0, then that would be fine. Or the way we teach it nowadays, now that we're not in the Stone Age anymore, is if we write it in scientific notation, you can write 9.0 times 10 to the second joules, and that way it has 2 significant figures. Or you can convert this into kilojoules. The problem does not specify what unit it wants, and so you could convert this into 0.90 kilojoules, and that number clearly has 2 significant figures as well.